Okay, so now we give the floor, so to say, to Martin Renoult, who's going to talk about his PhD work, and I'll let you discover what this is. It's really good for PMIP, putting PMIP into context. So off to you, Martin.
Thank you. I'm going to share. Do you see this well? Yeah, perfect. Okay, thank you for the invitation. So today I'm going to talk about paleoclimate perspective on Earth climate sensitivity. And so as Masa just said, this is a part of my thesis that I've defended 2 weeks ago. So climate sensitivity is today probably one of the most important metrics to understand future climate change. Essentially, it is a metric that considers the initial warming you will get out of the addition of carbon dioxide into the atmosphere, plus the long-term effect of climate feedbacks, which amplify and dampen temperature change. And if we look at the relationship that exists between the climate sensitivity of climate models, which are here, those colorful dots, and the warming they predict for the end of the century, you can see that there is a very strong correlation between the two across different scenarios of carbon dioxide emissions. And that shows how important it is to understand climate sensitivity for near future climate change. But unfortunately, understanding climate sensitivity has been a historical struggle for like more than a century. On this plot, I'm showing a range of climate sensitivity estimates from one of the first reports on climate change, so the Charney report in 1979, up to one of the most recent reports, which is the sixth assessment report of the IPCC in 2021. And you can see that for quite some time, the range of climate sensitivity estimates hasn't changed much. It was thought to lie between 1.5 and 4.5 degree. And it's actually only quite recently in the last assessment report that we can see substantial changes in the range, notably the 66% likelihood. And among the reasons why this range only changed recently is, well, first of all, we have less uncertainties on some climate feedbacks, for example, cloud feedback. But we also have a better understanding on how to put different methods together that constrain climate sensitivity. And one of these methods is to consider the information we get from paleoclimates on future climate change. So there are essentially two main approaches on climate sensitivity which use paleoclimates. The first one is maybe the most intuitive one is, we can call it the PaleoSense approach because I think it was made popular by the PaleoSense paper in 2012. It is essentially trying to estimate the forcing you have in a past climate associated with a certain temperature change compared to like a controlled state. And the other approach is, I think it's a bit more recent, at least based on paleoclimate, and it's the emergent constraint theory. It's a bit more statistical, and here we are trying to find a relationship that exists between two variables of the climate system that would exist in an ensemble of climate models, which are here, those blue dots. So in our case, we're interested in the relationship that can exist between climate sensitivity and the model paleotemperature to be able to infer the value of climate sensitivity by using an observation, so a geological reconstruction of some paleoclimate. So in this presentation, I'm mostly going to talk about, I'm mostly going to show outputs from emergent constraint analysis because it was the focus of my thesis. But I think the biases I will discuss are also applicable to more like the forcing-based approach you can find in the PaleoSense paper. So first, I would like to talk about past and present research using paleoclimates to constrain climate sensitivity, and those research mostly involve the Lasker maximum and the Pliocene, since there are a lot of simulation involving like PMIP and PMIP. And then I would like to talk more about the future research that can be done on this topic, and I will talk a bit about Miocene and maybe some other aspects that can be done. But first, I'm going to talk about the emergent constraint on climate sensitivity using last glacial maximum temperatures. So one of the first study to use it was in 2006. And then it was like really used in 2012 by actually, so this paper of Hargis et al. Using the full PMIP2 ensemble. And then it just went through with the different PMIP generation. Here on this figure, you can see an example with the PMIP2 and PMIP3 ensemble. So on the x-axis, you have last glacial maximum tropical temperature change relative to pre-industrial. And on the y-axis, you have the equilibrium sensitivity. And the blue line you see is what we could call the emergent constraint relationship. And by using an observed value here in green, we can infer a value of climate sensitivity here in yellow. So the issue that happened in, let's say, so in this paper 2014 is that despite adding more models with PMIP3, the uncertainty on climate sensitivity did not seem to get better with using last glacial maximum temperatures. And then when we go forward, here's a picture of one of my paper when I added PMIP4 models that you can see here in this like bluish color. And you can see that the quality of the correlation actually is just getting worse and worse as we go forward in PMIP generations. And when we look at the correlation that exists across the whole ensemble of PMIP, which is here, this black line, you can see the quality of the correlation is really poor. So today, we could say that the constraint we get on climate sensitivity from last glacial maximum temperature is now robust. It's not really robust, and it really got worse since PMIP2. There have been several causes discussed for this, and we can actually go back to Hargis et al. 2012. And from this correlation map that look at the local correlation between modal temperature and climate sensitivity. And so from this map, you can see that, well, back then, the tropical correlation was good because most of variation in climate sensitivity was driven by changes in tropical feedbacks. But as soon as you will go outside the tropics, the correlation was really bad already. So one of the reasons thought back then was because there was so much disagreement in ice sheet forcing that it will probably add a lot of noise in those extratropical regions. And another issue, for example, for the Southern Ocean, it could be that there was also some misunderstanding in like local climate feedbacks, for example, Southern Ocean feedbacks. And then moving on 2015, we have the Hopcroft and Valdez paper that looked also deeper into the causes of the weak constraint. And one of the causes that is shown on this figure is that when you do emergent constraint, you're actually comparing cold last glacial maximum temperature with climate sensitivity, which is usually diagnosed from warm simulations. And you should expect different behaviors in like just climate physics. So for example, cloud feedback between those two that can actually add uncertainty in your emergent constraint analysis. And it is also something that I looked deeper at in this recent paper, and I'm showing you on this map of total cloud feedback calculated from MPISM 1.2. And here I'm comparing 2 times CO2 from pre-industrial on the left and 2 times CO2 from last glacial maximum on the right. So it looks very like noisy, but you can actually see that there is some differences of pattern, particularly in this Pacific Ocean in terms of cloud feedback, but also in terms of amplitude. And for example, if you look at Northern America, so the Laurentid ice sheet, you can see clear differences in cloud feedback between the LGM state and the pre-industrial state. So it seems evident from this that cloud feedback can contribute a lot to creating noise and disagreement between models that would affect emergent constraint analysis. And that's just a part of all the issues we try to discuss in this paper. I cannot show all of them, but there are quite a lot that also connect to, for example, disagreement in ice sheet forcing and so on. And another issue for the last glacial maximum, it's a bit more geometrical, but it's the fact that you don't actually have very high climate sensitivity model in the ensemble. So if you look at this picture, you can see that there is only one, let's say, high climate sensitivity model, so a model with a climate sensitivity above 5 Kelvin, and that actually simulate a substantially colder last glacial maximum state compared to the rest of the ensemble. So here is CSM2, which is this, again, bluish color. And here it's quite a problem because CSM2 acts as a very strong outlier in this ensemble. So if you actually subsample the big ensemble, and then you make a difference between if those subsample have CSM2 or not, you end up with very different correlation that I'm showing here on this plot. So if you have a subensemble which contains CSM2, the correlation is always systematically good due to the outlier effect of CSM2. But as soon as CSM2 is not included, the correlation becomes quite bad. So I would say for now, the existence of CSM2 in the ensemble for this kind of analysis is a bit of a problem because it's unclear if we have a representation of high climate sensitivity model or it's just the behavior of that particular model acting as an outlier. And considering you have all this like cloud of quite messy model disagreeing all together, I'm not exactly sure that if we had one or two more high climate sensitive model, it would change like drastically the output we have currently. So overall, I would say the last glacial maximum is unfortunately currently not a very good constraint on climate sensitivity using emergent constraints. On the contrary, the Pliocene is much better. The Pliocene has been used more recently as an emergent constraint. So this is the study of Hargreaves and Anand in 2016, where they did similar analysis as for the last glacial maximum. Here we are looking at correlation map between Pliocene simulated temperatures, so within PMIP 1, and the climate sensitivity of those models. And here you can see that the correlation actually extends even beyond tropical regions, which is already quite a big difference compared to the last glacial maximum. And then if we look at just a scatter plot of Pliocene global sea surface temperature anomaly with the climate sensitivity on the y-axis of those models between PMIP 1 in red and the more recent PMIP 2 ensemble in blue, and also across the whole ensemble in black, you can see that the quality of the correlation is substantially higher than from last glacial maximum temperatures. And another interesting aspect here is that I'm using global temperature, and I still have a very good correlation, contrarily to the LGM, where global, the correlation is just non-existent, and tropical, it's actually not so much better. So the main issue with the Pliocene is not really the agreement between model, because they seem to behave relatively well together. The main issue are observational uncertainties, and it's actually becoming more and more challenging as PMIP is moving to a narrower time interval. So in particular, the time interval, the KM5C interglacial that is used as comparison with PMIP 2 simulations only has 32 data points in the world, which are also not evenly distributed. You can see there is quite a lack of data in polar regions and in the Pacific, which can add like a lot of uncertainties on the observational and geological reconstruction we have of the Pliocene. And this has obviously consequences when you try to estimate climate sensitivity from Pliocene temperatures. So here I'm showing an application of the emergent constraint theory with the PMIP 2 ensemble with all the models in orange dots. And I'm using a recent reconstruction, Pliocene temperature reconstruction, the Anand et al. 2022, which you can see has quite a big uncertainty range. And so consequently, the estimate of climate sensitivity is also quite large in uncertainty. And also something interesting here is that you can see the median value is also quite high. It's actually 4.8 Kelvin, which is in line with the other estimate provided in the IPCC, but it's quite on the high end. And something that could be hinted here is that maybe the KM5C interval that is actually chosen for PMIP2 might be biased high towards warm temperature. So here, for example, I'm showing where the KM5C interglacial benthic delta weighted and CO2 locate themselves within the whole Pliocene, not exactly, within 300,000 years around the mid-Pliocene. And you can see that actually those stars, which are KM5C proxy values we have, they actually match, they correspond to relatively high benthic delta weighting, so relatively warm temperature for not so high carbon dioxide value, which would obviously bias high climate sensitivity estimates. So overall, I would say that Pliocene constraint on climate sensitivity is still a bit hindered by all these observational uncertainties we have. In this paper that is coming, we also discuss more structural issues that I also unfortunately don't have time to talk about. But I would say all in all, the Pliocene constraint is very robust. And I really believe that it will become better as geological reconstruction improve in the future. And so now I would like to talk a bit more about future work that can be done on this aspect. And I think probably the future paleoclimate that will be used to constrain climate sensitivity will be the Miocene and the upcoming / ongoing project PMIP. So I think the Miocene will have very similar advantages as using the Pliocene in the sense that it's a very warm paleoclimate. So you should expect similar behavior of climate feedbacks between the Miocene and 4 times CO2. Perhaps one of the problems of the Miocene is that they are substantially different paleogeography compared to pre-industrial, and you have like really big differences of ocean circulation that will probably add a lot of noise in the emergent constraint analysis, and that could probably bias more climate sensitivity estimates. But I still think it will be a very, very interesting work, particularly to compare to what currently we have from the Pliocene, to have a better indication of what paleoclimate, warm paleoclimate, tell us about future climate change. And I will be very happy to do this work if I have access to the Miocene simulations when they are available. And I think there is also something that is really worth considering is how to actually combine all those evidences we get from paleoclimate. This is something we tried to do in 2020 by combining the evidence on climate sensitivity we get from last glacial maximum temperatures and the one from mid-Pliocene temperatures. And usually what you will end up is you will have a much narrower final value of climate sensitivity when combining those climate together. And I think there's a lot of work to do here. I think it would be very interesting to find better ways to combine all those different evidences we can get in the future. So for example, with Miocene that is coming. And I haven't talked about like other paleoclimates such as the Oligocene and the Eocene, where there could be also some future ensembles. But I think they're less interesting as you get further in time because they might be less representative of future climate change. But I would be very happy to discuss this. And so on this, I would like to conclude and summarize what I just talked about in this presentation. So in this presentation, I mostly showed like that, yeah, paleoclimates can be used to constrain climate sensitivity, mostly in emergent constraint framework, but this kind of biases you can have, for example, disagreement in climate feedbacks, they are also probably affecting more like forcing-based approach. It seems that currently the last glacial maximum provides a weak constraint on climate sensitivity. On the contrary, I think the Pliocene provides a robust constraint and is very likely to improve. Currently causes of this kind of weak constraint are like intermodal disagreement on climate feedback behavior, and probably also some structural issues in models, some observational uncertainties problem, and so on. And I think future work are probably going to include the Miocene, hopefully. And maybe some older paleoclimate, maybe the Oligocene could be interesting, or maybe some different time slices within the Pliocene. And as I just said, I think definitely finding better ways, finding better statistical ways of combining paleoclimate together is definitely worth investigating. And so on this, I would like to thank you for listening.
Thank you very much, Martin. I think we can have one question of understanding here and then keep the other questions for the general discussion after that. There's quite a lot of discussion you will discover in the in the chat already. But if somebody has an urgent question for Martin, please switch on your camera and microphone. Right, there is a question from Andreas in the chat. He's wondering if failed, unstable simulations could still be used to constrain ECS because they indicate that high ECS are unlike, but it is difficult to include them in a formal quantitative analysis. This actually follows up the discussion that some models have had a hard time to actually run their LGM.
Yeah, I think it can be very informative on what could be the maximum climate sensitivity, like really the threshold value you should not go above. If you don't know what to do with them, I have some work on Snowball Earth that would be very interesting to get those simulation if you have them. So yeah, I think there are ways. So keep them, keep those simulations.
Okay, thank you very much. I think we can go to Alan now, and then thank you, Martin, again for this very clear talk. So now we can go to Martin, who's going to tell us more about LGM, I guess. Off to you.
Great. Okay. 1 second. Okay. Ooh. Can you see this okay?
Yes, perfect.
Okay, great. Turn on the laser. Okay, cool. Great. Well, thanks for the invitation to share some of this work, and thanks everyone for being here. And I'm looking forward to a nice discussion after this talk. So today, as you can see, I'll be talking about the land-sea temperature contrast under a wide range of climate states. And I want to start off by showing a time series that's probably familiar to most of you. This is the increased warming over the land surface relative to the sea surface since the Industrial Revolution. And in this talk, we're going to be referring to this as terrestrial amplification, or TA. So you'll see that a lot. And the goal of this talk is basically to ask the following question of whether paleoclimate data can help us to validate and improve a fundamental theory for why terrestrial amplification exists. So I've basically broken the talk into 3 parts. The first one is going to be to introduce a pretty simple dynamical theory for TA. The second is going to be to quickly dive into some LGM proxy systematics and constraints on fast cooling. And then finally, we'll compare this theory and these proxy constraints to PMIP4 LGM simulations and also to CMIP6 simulations of future warming. Okay, so we'll start here. What you're looking at here is a figure from this really nice paper by Joshi et al. 2008 that showed an increase in warming over land versus sea surfaces. So this is the warming ratio in a bunch of transient simulations. I think these are CMIP3 models under the A1B emission scenario. The details aren't particularly important, but what's important is that each of these models, right, shows a value greater than unity. So there's amplification of warming in the global mean. And we can also see that the transient simulations are pretty similar in magnitude to these squares you see on the right. Those are from equilibrium slab ocean double atmospheric CO2 experiments. So the point here is just that terrestrial amplification in models shows up in both transient and equilibrium simulations. And so it's not a simple consequence of the difference in land-sea thermal inertia. There's also a large spread across models for the global mean warming ratio. And so for most of this talk, we're going to be looking at the low latitudes where this pretty simple theory applies. So what is that theory? So today I'm talking about a theory put forward by Byrne and O'Gorman in 2018, but it really builds on several decades of work that came before them. And it hinges on two basic constraints. The first is a moisture constraint, which basically says that specific humidity changes over land surfaces should be proportional to changes over sea surfaces, right? And just as a refresher for those who might not think about this all the time, right? Q, or specific humidity, is just the ratio of the mass of water vapor in a parcel of air to the total mass of that parcel. And the second constraint comes from dynamics in the low latitudes, where moist static energy changes are equal over the land and sea surfaces through convective adjustment. And I'm going to go into the origin of both of these constraints in a moment, but here just to introduce this concept of moist static energy, we're thinking about these three terms, the first being sensible heat, the second being latent heat, and the third is geopotential height. And that'll become important in a moment because it has to do with sea level changes in the LGM. So this isn't a new idea in any sense. So as far as I know, the first paper to link evaporative changes or specific humidity changes to the land-sea contrast was Manabe et al. In 1991, who ran transient and equilibrium simulations, found terrestrial amplification, suggested that it was related to the difference of the capacity of the land surface to change its latent heat flux relative to the sea surface. And if we fast forward a couple of decades here, there were two papers that came out in 2016 that effectively independently suggested the same idea, that changes in land surface specific humidity should be coupled to the sea surface changes in specific humidity with this constant of proportionality that's less than 1. And so what Chadwick et al. 2016 did is they looked at the CMIP5 mean changes in surface specific humidity under the RCP 8.5 pathway. That's what you're looking at here. And you can see it increases everywhere in the globe, of course. And what they did is along a line of latitude, so in the zonal mean, they took the ratio of future specific humidity over the ocean to present specific humidity over the ocean and multiplied present day land surface specific humidity by that ratio. In other words, just to test whether this constant scaling could work. And indeed, they got really similar results between the actual simulations and this really simple scaling model. And then in that same year, Byrne and O'Gorman 2016 introduced a simple box model approach for thinking about terrestrial amplification that's built on the same fundamental assumption here, this scaling of land surface and sea surface specific humidity. And they ran a bunch of simulations and tested how well this simple theory did. So the dashed line is the theory and the actual simulations are these lines with the open circles. And as you can see here, what's interesting is that they were able to demonstrate, and they gave some good reasons why this is the case, but they were able to demonstrate that the theory should be effectively insensitive to climate state and to changes in circulation. And so you can see that this dashed line nicely reproduces the solid line between, let's say, a global mean sea surface temperature of 270 and 300. So relevant for the LGM and also for future warming. Okay. Quickly moving on to the second constraint, just to develop some intuition for where this comes from. The idea is that under a warming or a cooling, you have a change in moist static energy over the oceans. And through convection, that's transmitted to the free troposphere. And in the low latitudes where the Coriolis force is weak, there's really efficient homogenization in the free troposphere. And through convective adjustment over land surfaces, we end up with the same change in moist static energy. So the idea is that in the low latitudes, at least, changes in moist static energy should be the same over land surfaces and sea surface. Just for fun, I wanted to show that we can actually see this in modern data. So if you're looking here at ERA 5 reanalysis data from the low latitudes 30 south to 30 north, at the surface, there's this obvious contrast in temperature. Land surfaces are warmer. But as we move up higher into the atmosphere, right, we can see that in the free troposphere, the zonal gradients are smooth. Okay, so if we put all this together, this humidity constraint, the energetic constraint, and the moist static energy constraint, we can derive the fundamental terrestrial amplification theory of Byrne and O'Gorman in 2018, which looks like this. And just to develop some intuition for what this actually means, we're saying that a land surface warming or cooling is equal to a sea surface warming or cooling plus these two terms, one having to do with moisture changes and one having to do with geopotential height. And so for future warming, this delta Q naught, or the change in sea surface specific humidity in the low latitudes, scales with the change in temperature over the oceans, right, with the Clausius-Clapeyron relation. So something like 6% per degree in the low latitudes. Gamma is less than 1, and that makes this a positive value. And for near-term warming, changes in sea level are not appreciable. And so you can see that if this is positive, you get terrestrial amplification fundamentally from this theory. Okay. This 2018 paper also tested this theory using modern observations, and you'll note that they're fairly noisy, and of course the amplitude of the modern record is small. That's a great reason for doing paleoclimate research, right? But this theory, which is the open circle, really nicely reproduces the warming trend on land, the difference between warming over land surfaces and sea surfaces, as well as the differences in specific humidity changes and the reduction of relative humidity over land surfaces. So again, where we're going here is to ask whether paleoclimate data can help us to validate and improve this theory. And specifically, what we're going to do here is ask what gamma value is implied by LGM proxy reconstructions. How does this compare to PMIP4 simulations of the LGM? And then, is it insensitive to climate? So do we see the same thing show up across climate models, both in the past and in the future? So to do this, we have to think about the change in sea level in the LGM. And I think this is an important point, and maybe something we can discuss in the Q&A. But because the sea level was lower in the LGM, there was a reduction in the geopotential height component of moist static energy over the sea surface. And as a result, for the same given reduction in moist static energy, less of that is associated with the change in sensible heat, meaning that there's sort of this anomalous warming, you could say, of the sea surface in the LGM because of lower sea level. So to do this, to test this theory and to come up with a distribution of gamma values, that constant of proportionality between land and sea surface specific humidity, we're going to take ocean surface cooling from Tierney et al. Data assimilation reconstruction. I know there are other choices out there too, but one thing I really like about this approach is that it uses an isotope-enabled GCM, and that allows for direct proxy comparisons of delta 018, for example. And then for land surface cooling, we're going to use a compilation of land cooling estimates from noble gases dissolved in groundwater. So I'm going to take a minute here and quickly introduce this compilation and this proxy for those who might not be familiar. The idea basically here, right, is that there are noble gases in the atmosphere. They're inert and chemically and biologically, right, unreactive. They're spatially well mixed, so the concentrations are the same at the North Pole, South Pole, and the equator. And there are no sources or sinks on glacial and interglacial timescales in the atmosphere or in the subsurface. They dissolve into groundwater at the water table, and that dissolution is a function of temperature, the well-known physical solubility function. Of course, then there's subsequent recharge in an aquifer. There's flow away from the recharge area. And at some point in the present, we can drill a well, collect a sample, date it with radiocarbon, measure noble gases, and reconstruct the annual surface temperature. But how does this actually work, right? So we have noble gases in the atmosphere that enter soil air. They dissolve at the water table, right? Some fraction dissolves, and that dissolution is a function of temperature. And so in colder water, there'll be more dissolution, right? So that's the basic concept. Colder temperature, water can hold more dissolved noble gases. Another nice property of this proxy is that the water table typically sits a few meters below the land surface. And so seasonal temperature fluctuations are damped by diffusion of heat in the subsurface, such that mean annual surface temperature is often recorded. What we did a couple of years ago in this paper was to compile all of the existing noble gas data over the last few decades that from regions where there was LGM groundwater. Turns out there are a lot of areas that have LGM groundwater. And just to sort of illustrate this point, if you just look at the xenon concentration in all of the late Holocene or modern groundwater and compare it to recharge site temperatures today, if this is the expectation for solubility equilibrium, these are the actual data, right? So you certainly see this, but there's some scatter. And a lot of that scatter has to do with the actual physical processes of dissolution in bubbles. And so what we do is we actually measure neon, argon, krypton, and xenon together. And through least squares, we constrain a physical model that includes temperature. And that gives us a really robust estimate of temperature. And if we actually look then at noble gas-derived temperatures and compare them to modern temperatures around the globe, we see a really nice, clear relationship that seems to work very nicely throughout a wide range of temperatures. Okay, zooming forward to the LGM, we have all of these records from the low and the mid latitudes that together suggest something like 5.8 degrees of cooling on land. If we restrict this to from 30 south to 30 north, it's actually, there aren't that many records. There's something like 9 or 10, you get something like 5.9 degrees. And that's obviously more than the 3.5 that's suggested by the Tierney et al. Reconstruction at the sea surface. So what are we going to do here? We can take this Byrne and O'Gorman 2018 equation and we can solve it for gamma. Looks like this. I'll leave the algebra to you if you want to check. But basically, what we can do then is we can plug in an estimate of sea surface cooling, an estimate of land surface cooling, account for the change in sea level, and then account for the reduction in sea surface specific humidity in the following way, right? Where we can take the modern sea surface specific humidity and multiply it by the fractional change per degree of cooling from the Clausius-Clapeyron relation. That's what this is. And if you do this, you get a value of 0.82 for gamma. So what we actually did in this paper that's currently in press, and I think it'll be out next month sometime, is we did a Monte Carlo analysis and some sensitivity testing, thinking about potential small changes in relative humidity over the sea surface as well. And we ended up with this distribution of plausible gamma values based on these LGM proxies that ranges from about 0.73 to 0.94. So is this consistent with PMIP4 simulations? Right, so what we're looking at here is the magnitude of land surface cooling in the low latitudes on the y-axis, the magnitude of sea surface cooling in the low latitudes on the x-axis. This thick black line is the one-to-one cooling line. That would be no terrestrial amplification. And then all of these dashed lines are different theoretical predictions for different gamma values. Okay. Here are these proxy constraints and a shaded region that corresponds to that distribution of gamma values according to this theory. And I want to take a minute here to point out that, of course, there are other proxy reconstructions, right? We've chosen the noble gases because they have this, physical and direct link to temperature, but of course, there are other records that have much better spatial coverage. All proxies have their strengths and weaknesses, and I'm sort of hopeful that this community and maybe spurred by this really nice webinar series that's been started really has a chance to come together and make some progress on this. One thing I will note is that this previous set of proxy constraints, one is from the Margot SSTs, and the other is the Bartling pollen reconstructions. There's a new pollen-based data product, and I'm not an expert in this, but maybe we could discuss later, that seems to show 5 degrees of cooling at the land surface, which is much closer to the noble gases. So anyway, it's an interesting discussion to have. We compare this to all of the PMIP4 models, we indeed find that there's terrestrial amplification in all of them. And most of them fall between this range of about 0.8 to 1.0 implied gamma values. These ones that don't fall in that range are actually pretty interesting. And we've done some work looking at the structure of pressure changes in the LGM atmosphere. Not all of the models have that available. So if you have some from your model and you want to share it, that'd be interesting. And also it may have something to do with the way that sea level changes are parameterized. So, but the point is that TA appears in all of these models, and for most of them in a range that's really consistent with the proxy constrained gamma values. In other words, even if the models have different dynamics and different amounts of cooling during the LGM, they all seem to follow this simple fundamental thermodynamic expectation. And then to wrap up, we can quickly look at how this prediction does for the future. So here you have land surface warming on the y-axis, sea surface warming on the x-axis. And what we can do is this shaded region here is the theoretical prediction from these LGM proxy constraints. And because this theory should be insensitive to climate state, it's kind of an interesting way where we can actually take constraints from the LGM and try and say something about the future. So if we compare this to CMIP6 model estimates of warming under abrupt quadrupling of atmospheric CO2, we see the following, right? So we see values that are kind of consistent with a gamma value of about 0.8 on average. And if we look at the SSP 5 8.5 pathway, we see, of course, less warming, but also values that are sort of in that range. And so together from LGM proxy constraints and from these model simulations, we're able to sort of narrow the range of likely terrestrial amplification, at least in the low latitudes, to something like 40% greater warming over land surfaces than sea surfaces. And so it basically supports the idea that this theory may indeed be climate insensitive, and that terrestrial amplification certainly does show up in this range for future warming. So to wrap up, we've introduced this, or we've expanded this theory that's been several decades in the making by a lot of great work that came before us, to think about the LGM. It seems that, at least to first order, it is equally valid under different climate states, which is interesting. And we're able to use paleoclimate proxy data to sort of bolster model predictions of future warming and of course drying, because of the moisture component of this over land surfaces in the low latitudes. But of course, there's a lot more work to be done, right? So some questions that I'll sort of pose to the group, I'm happy to chat about, whether in the Q&A or over email, or can we learn more from regional differences? This noble gas proxy is really useful, I think, but we don't have that many records, certainly not compared to all of the great proxy or pollen records and lake sediment records and other terrestrial constraints that we have. So, can we make progress by combining proxies and making the best of their relative strengths and weaknesses? Are there improvements in data assimilation? I know there have been some interesting work done recently on thinking about, the sensitivity of data assimilation reconstructions to model priors, right? So, I think this community can really work together and get a better view into regional differences beyond just lumping the whole low latitudes together, because they probably inform important dynamics, right? Another thing that I want to point out is that it's really important to think about sea level change and its impact on the warming of the sea surface in the LGM, especially for equilibrium climate sensitivity estimates. Martin pointed out, right, that we still have a lot of work to do if we're going to be able to use the LGM to say something about climate sensitivity, but this is another thing to think about. Can we learn something from past warm periods, right? So are there proxy and model constraints on the land-sea contrast in the Miocene, for example? It's well beyond my area of expertise, but I'd be interested to chat with those of you who might be interested. And finally, outside of the low latitudes, the land-sea contrast is interesting and probably more complicated. And are there ways that paleo constraints from models and from proxies can help inform dynamics? So with that, I'm happy to wrap up and take any questions. And if you have anything you want to discuss, any ideas, please feel free to send me an email. So thanks.
Thank you, Alan. Thank you very much. There's been quite a lot of comments on both talks in the chat. And so I'm opening the floor for questions, discussions, so on and so forth. And if the PMIP Wings organizers can help me finding out who wants to talk, that'd be great.
What do you want people to do? To raise their virtual hands?
Yeah, I think they can raise their hands.
I think they're on the top of the list of the participants.
Can probably unmute themselves as well. I'm not sure. Well, you did, so yes.
I've enabled that, so everyone can unmute.
So don't be shy. And who wants to start?
Otherwise, I might call in to ask a provocative question and hope to raise also the interest of the participants. So which one of the constraints or which one of the time periods is now going to be more relevant, the LGM or the Pliocene or the Miocene? And will the Oligocene really help us, given that we're going even further back in time to a different carbon cycle and paleotopography?
Should I answer that question?
Go ahead, maybe somebody else starts shouting.
I think the Pliocene probably is the most promising one. The LGM has a bunch of problems. The Miocene, I think, might be an issue because the thing is, the more you changes the paleogeography, the more freedom you give to models, and so the more space you give them to disagree. So I think as we go back further in time, it will become more and more problematic. I still think it could be interesting. The Miocene is not that far. And you probably have some, I think the thing is that is interesting with the Miocene, so you also have a stronger temperature signal. So you might also have a better signal to noise ratio. So that could be, but I would say the Pliocene is probably the most promising. I don't want to hurt any LGM scientists, but I think there is a bit of work to do on the LGM so far. And I think the Oligocene is not, you cannot consider this. It starts to be too far in time.
Yeah, if I may jump in, I think it obviously depends on the question you're asking, right? So for climate sensitivity, it's obviously really complicated, right? But I think there are some more specific dynamical questions we can ask, and shifts in the storm cracks, for example, right? Things like this that I think the LGM is really valuable for, and I don't think it should be overlooked. Just how much more data we have available, from land and from sea surfaces in the LGM. So, I mean, I think there's a place for all of these different time periods, and but I think it really depends on the question you ask.
And I would say actually, even if the constraint doesn't look good, I think it's still very valuable to do those constraints, because I think you still learn a lot. Like doing all this paper, we learned a lot on how the Lasker maximum is being simulated, and you learn a lot on the physics of the Lasker maximum, and that actually inform a lot on future simulations. So it doesn't constrain very well the climate sensitivity, but it might be very informative on future things that should be done for paleoclimate and like climate models in general.
So Martin, you're saying it does, your LGM simulation did feed back into your model development in an iterative way?
What do you mean? I'm sorry, I don't understand.
So the whole point of doing the paleo constraint is a way to, well, you could do a one-off, like this model did well, this model did poorly, and I've constrained ECS across these models, or you could say, oh, I'm going to do some constraints on my model by having a feedback, like my model did a really bad job at the LGM, and I think it's because of this thing, and you do that thing and it looks better, and then it would be a mechanism to feedback. That's what I'm asking, like that tie-in. Sorry, it's Allegra talking. Sorry. Yes.
I think it depends what you're trying to do. I think if you're trying to change a model just to improve a correlation, I think it's not the proper way of solving the problem. I think if you're trying to solve the problem because from proxy observation that aspect of the Lasker maximum should be fixed, then I think that's the way of doing it.
So you'd be more like, oh, we saw like our LGM spur that had the dust did a better job, so therefore we know we need to have interactive dust in the future, something of that order?
Yeah, I would think something like that. But at the same time, I'm like, at least for my question, I don't know what is a bad model. For example, CSM2 has been highly criticized, but I think what they actually did is spectacular. I mean, they have a very, very cold Lasker maximum, and it doesn't seem realistic in terms of like geological observation, but it is consistent with its climate sensitivity, and I think it's fantastic.
Their super cold thing, like there's all those Zhu papers where they went back into their clouds microphysics and they're like, whoops, and maybe that was actually too high ECS. Oh, guess what? ECS is not that high.
Yeah, also they had this.
That's the feedback.
Yeah, well, that is a really nice example of like you really missed the boat on doing the paleo simulation, and it caused you to ferret out a gnarly bug deep buried in your model code.
Yeah, but then I think here it is really because they realized that there were some issues with the model or the physics. They didn't do that in a way to improve a correlation, or because that would bias, I think, your statistical like thoughts or something.
But I mean, that's what groups do for the present day. They have like, oh, here we have these 50 different satellite and other observational networks, and yeah, only these versions of our model look reasonable constrained across these observations. So the models, I mean, that process is in itself biasing?
I mean, it's weird, no? It feels a bit of like choosing something to have very specific results, I would say. I'm not sure. I'm not familiar with satellite and so on. So
do you want?
Very nice job, by the way. Sorry, I should have led with that. Nice job, nice work. Pardon, nice work, Alan.
Any sorry, any other topic that you want to raise? There was some talk about gathering all these failed LGMs, which sounds funny, and maybe we should gather, of course, about this.
I feel like before Masa, we would see each other periodically and you would say, oh, we're having trouble with our LGM. And like, we think it's like maybe this problem. And I would say, oh, we're also having problems. And there was a lot of word of mouth communication, which I love the Zoom stuff, but yeah, it would be nice to have maybe a written record of those kinds of things.
We could have probably a small written page somewhere where we give each other's news about our LGMs. There won't be an IPS LCM6 LGM, but there might be an IPS LCM7 one. Going back to Alan's talk, I think it's interesting to see. So you have these differences in the reconstructions from the different proxies, and I think that would be really nice to go back on this and try to understand those first, and maybe find some consensus or some ground of some better way to know about the tropical values, or in other places. What do you think, Alan? I think I've seen Bart somewhere. Maybe he's left already, but I think there's a...
Yeah. Yeah, I have a lot of thoughts on this. You know, I think one thing that's useful about just having this framework to think about how land and sea surface cooling should relate is that it sort of tells us what combinations of proxies are sort of plausible, right? And so, you know, for example, you know, now it seems like there are several proxies that show, you know, 5 or so degrees of cooling on the land surface in the LGM, right? And we can see then, you know, that that's consistent. And I guess I have to pull out my calculator to see exactly, you know, what the range is with different gamma values. But basically, you know, it implies that you probably need something like at least 2 degrees of cooling of the sea surface. So probably one degree is not enough, but then, you know, 4 degrees would be way too much, right? And so I think these sorts of things are helpful in starting to at least have a physical basis for comparing these records. But you know, I think in terms of actually making progress, I don't know how many proxy people are here, but you know, I think that one thing that I think would be really promising would be to pick a place. And of course, I'm a terrestrial paleoclimate scientist, so there are probably ways you could do this, and it has been done in the ocean. But on land, you know, could we find a place where there's groundwater and there's you know, pollen records and lake sediments all in the same area, right? And can we just compare them? And are there, you know, can we make the best of the different strengths of the different proxies, right? The noble gas proxy is physical and direct, but it's hard to date and it's low resolution and there aren't that many of them. So, could we get the amplitude from noble gases, for example, in certain areas and scale pollen records or something? I mean, just an idea, right? But I think we got to find ways to work together because that'll give us a much clearer picture of what the LGM actually looks like.
Right. Many ideas for collaborations to come, and we are getting close to the hour of webinar. Are there other comments to be done? I see sometimes people coming in and out on their videos, so I wonder if they if they want to talk, but I'm not sure. So please talk if you want.
Well, just the thing I just wrote in the chat that we would like it if people would volunteer and volunteer other people. Let us know who's done something interesting and it can be anybody who is interested in paleo, PMIP sort of related things. And so, because we'd rather not be having to invite people all the time. It seems a little bit cliquey if we do that. I mean, I didn't invite Martin, so I was embarrassed how many times we were mentioned. But yeah.
That was the first, so we organized a little bit, but we hope that it gets rolling by itself. We have one volunteer already. So, well, if there's no other question, I would like to thank you for the quality of the talks and discussion and